This is a walkthrough of a workbook I have made as a part of the Houston Machine Learning and Material Science workshop. I'm Stephen Kawe, and at the workshop, I gave you an outline of the general steps you'll need to take in order to do machine learning, and I showed you Pythonic ways of implementing that. What this is a supplementary video for you to go back and hear again from me exactly what each line is doing and why we did it the way we did. So to start with, the first thing we're always going to be doing if we're working in Python is importing libraries. These are sources of code that other people have worked on for a long time, a lot of them but better programmers than us, and they allow us to do a lot of complex things very simply. Now, really quickly, without going into too much detail, we're going to import pandas, NumPy, and matplotlib. These are sort of like general Python libraries that most people use. Pandas is good for Excel type stuff. NumPy is good for mathy things, especially if you're working with like arrays, vectors, or matrices. And matplotlib allows us to plot things really quickly and easily. In terms of the machine learning, we have these libraries here. They're all coming from sklearn library. We have the model selection module. There's a train test split function. This is going to allow us to take whatever data we have and make a train and test split. We'll talk about that. This allows us to do k-fold validation. We'll talk about that. This allows us to do grid search. Again, we'll get there. Now, before we do any sort of machine learning, if our algorithm, so a word you're going to hear a lot, if our machine learning algorithm requires what's called gradient descent to get a solution, we're going to want to implement some sort of scaling. Here, I'm going to be using standard scaling and normalization. This will perform an operation on the columns, or rather, it'll make our features scale to each other, and this will normalize the vector for each instance of data, so no vector is more important than the rest. And then finally, in this work, we're going to use a support vector regression to predict properties. This is the algorithm we're choosing, the machine learning algorithm. There are many choices we could have made here. This is one of them that I know works well. You could play around with this on your own. And then once we've made predictions, we're going to want metrics to see how well we did. So we're going to import R2 score. That's like the coefficient of determination. That's your classic R squared. And then a mean squared error just to get a general idea how we're doing in raw numbers. And we'll probably take the root of that. So it's something we can compare units wise. Then finally, I've written some code that I think is a little too complicated to go over here. One is composition. This is a Python file. If we go to our file explorer, it's this one right here, composition.py. In fact, we can even open it up. It just has some functions for parsing chemical formulas and vectorizing those formulas. And then the other one's utils.py. Utils has some plotting functions in there, just some things that are kind of ugly to put inline in your text, but are useful to make a good figure. I'm just going to go ahead and restart this kernel so we can go through all of it from scratch line by line. Don't worry about these errors. This IPython kernel has a small bug that needs to be taken care of. Okay, so I'm going to close these for now. We can open them if we need, but that's what we're doing here. We're importing those two files so we can use functions that are defined in there. Okay, so the first thing we're going to want to do if we're going to want to do machine learning and material science is find data. To find the data, I made a YouTube video where we go to the AFlow database, we do a quick query, and we copy all of that data into a CSV file. And I saved that CSV file into this AFlow data folder. So this is the directory I'm working out of. This is Ubuntu, so you might not be used to it. But essentially, it's just the folder where my main code is, machine learn elastic properties, as well as information that code's going to want to access. So it wants to access these two files on the import. We're going to want to read in this data eventually. So this is my directory, or the folder that my main file is in, right here. Okay, so once we have that AFlow data, we're going to want to go through and clean it. If we open this data up, we'll notice that it has an entry, and in it is this chemical formula, but it also has this giant AFlow ID attached to it. We're going to want to get rid of that first things first. We're going to clean our data here. So in order to get that data, we're going to read in. So we're going to use pandas, which is abbreviated up here as PD. So we're importing pandas with the abbreviation PD. So we're going to use pandas to read the CSV. This section, we're going to reach into the folder AFlow data, and then we're going to grab the file aflow_elasticdata.csv. So right here in our variable explorer, I'm using Spider. You'll notice there's no variables in here, but when I run this first line after doing the import, so first I'm going to highlight this and hit F9 to run all of these imports. So when I run the first line, my cursor is here on line 42. If I hit F9, it's going to run that line. Now I can look up here. df aflow elastic. So that's this variable right here. And on it is saved a pandas data frame. That's the type here of size 2382. So that's the number of rows with 8 columns. So if we look at this, we can expand it out. We have our entries, which is our chemical formula plus some aflow unique ID. And then we have the composition's properties. So here's the bulk modulus, the elastic anisotropy, the Poisson ratio, shear modulus, and then some crystal system information, space group, Pearson symbol, which has like cubic. I can't remember exactly what all these mean, but all important stuff that we might be able to use later. And then where it came from, this isn't really useful to us. These used to be links in the original, on the original website. When we copied them as plain text. So now that we know what it looks like, let's go ahead and close out. But we're going to be wanting to deal with this entry column, and we're going to want to parse through it and intelligently remove this second half where there's this extra information. So to start with, I'm going to save a series. So each column, each set of data in a pandas data frame, each column is called a series. So I'm going to run this next line here. And we're going to get the specific column named entry. Notice there was a space after it when we grabbed it from the aflow database. We're going to grab the specific column called entry. It's now saved onto, that column is saved onto this variable, uncleaned formula, as a series. So again, it's just a column, a single column by itself. And you can see it's 2382 by no dimension because it's not defined along. There's like, we're not saying how many columns it has. We're just saying it's a series. So you can open that up, and similarly, just like the single column we saw there, same thing, same thing. Okay, now that we have that, what we're going to do is we're going to loop through this thing. Right here, we're going to do a for loop. We're going to loop through this variable, through the series with all of these different data entries. And as we go through it, we're going to use a string function. So when I loop through it, let's go ahead and look at what a loop looks like. In my console down here, I can say for cell value in uncleaned formulae. And let's just run this from like 0 to 10. Just grab the first 10 instances. We can print cell value. Let's see if that works. Okay, so it printed out for each value in the first 10 instances of my series, print out that value. So let's go ahead and just look at what this looks like by itself. We'll copy this and just run that single thing. So this is just the first 10 entries of our series. So if we look down here from 0 to 9, it matches up to here. Perfect. So there we go. And if we wanted to look inside of this entry, this is actually a string, this data type. So what we could do is for value, here, let's go ahead and copy this again. We'll just iterate through one or two of them. So from the first instance to the 5th instance is fine. We can say cell, you know what? Yeah, we can say cell value equals, or sorry, cell equals cell value. And we can look at what cell is up here in our variable explorer. So cell is a string type of size 1. So we're working with a string. And I did all of that to show you this part here. So cell value, I could have just used cell value instead of doing this silly redundant logic. Cell value is a string, and this is the string's value. So if I go here, I'm actually doing an operation on a string. So if I do that, we could do first name, last name, instead of actually using the variable cell value. And we can do split out of space, and what it returns is a list where that list has been split at the specific character we told it to. So in our case, what I'm doing is I'm taking the string cell value, which is AG1 IN5 SE8. I'm telling it to split at the space left square bracket. So if we run this here, we can see what the output is. It's going to be our formula on 1/2 in index 0 in the first instance of the list, and then the aflow ID with the extra square bracket as the second instance of the list indexed at 1. So to grab this formula, which is all we care about, I'll say my clean formula is the split, or rather the list that resulted from this split in index 0. So it's going to be grabbing this one. Now every time we go through this loop, we're going to start by grabbing this first one. So cell value will have the value of this line here. Then the second time through the loop, cell value will take the line of this here. Third time through, cell value will take the value of this line here. So as we loop through this list, or as we loop through this series, we're going to get a clean formula for each line. And then we are going to append that clean formula to this list of clean formulae. So let's go ahead and run this here and see what we get. So clean formulae, this is the unclean version. It has 2, 3, 8, 2. So then we can look at the clean version and we can compare the difference. So notice first off, this is a series, whereas this is just a list of string values. And then second off, notice this doesn't have the aflow ID, just like we wanted. So we did the first task of cleaning this pretty well. Okay. Now that we have the cleaned version of the entry column from our aflow data, we can go ahead and make a data frame that we'll call gfCleaned. So we're going to initialize an empty data frame here. And to that data frame, we will add the column named formula and give it the values of cleaned formula. So now instead of entry, where we have sort of this messy representation of our chemical formula, we will have simply a column named formula with the formula that belonged there. Similarly, in that cleaned data frame, which was empty, then had one column named formula, we'll add a second column named bulk modulus, and we'll use our other data frame, df_aflow_elastic, and we'll access the bulk modulus column, and we'll say df_cleaned is going to be equal to the same values as this bulk modulus column. So we come back over here and we see these values are going to be matching the bulk modulus values. So if we come here, they're the same. Perfect. Okay, so that's it for cleaning the data. If we want to evaluate the data, if we want to look at it and play with it, we're actually most of the way there. Cleaning the data took a little bit of logic and a little bit of thinking on how to split this string. Not too much, but a little bit, especially if you're not used to Python. Evaluating the data is going to have some easy function calls that are useful to know, and we'll go over them. So the first things first, we want to check to make sure that our data does not have duplicates. And if it does have duplicates, we know how to handle them. So an example of a duplicate would be alumina appearing twice in our data set. Al2O3, and then the next instance of data is also Al2O3. So imagine if we had this same one twice in here. So we can check, if we go to the formula column, this is going to be a simple way. We're just going to match the strings. That's, of course, not perfect, because something like Al2O3 and Al406 might slip by, where it's just a multiple of each other. But we'll just match the strings directly and see how that works out. So to do that, we're going to look at our clean data frame in the formula column, and we're going to get a value count of it. Okay, so if I run this, what this returns is instances of data from that column and how many times they appear in that column. So here we see that there's quite a few duplicate values, where this specific string appears twice in that column. So if I run this again, we can look at the actual series that's returned for check duplicates, and we can kind of just, skim through here and see what's up. So not a ton, but there's a few, small fraction of our data with duplicate values, and there's no more than 2 of them. So an easy solution to get rid of this is to just drop all of the duplicates except for the first one. So in our data frame, we're going to drop duplicates in the column formula, keeping the first instance of it, and we're going to do it in place, meaning our data frame, df cleaned, is going to actually change. So we're not going to return a copy of this data frame after we've dropped the data. We're going to change the data frame itself. So the object is going to be augmented by this function here. When I say object, it's like what's in the memory of the computer, what this variable represents is going to be changed by this. Okay. So if we run this, we're going to look, it goes 2382, and we run it, and it drops down to 2336. So about 50 of these had duplicates. Great, so that was a simple solution. Now you're going to say, well, that's a simple solution, but maybe we want to do something more pretty, like taking the mean. We can do that, but for now, I think it's worth, you could Google that. For now, I think it's worth just moving on. So after we've removed duplicates, it's also probably useful for us to look at the actual distribution of the data. So we're just going to be checking for anything odd. We can think to ourselves, okay, does this property allow negative values? What do we expect the mean value of this property to be? And what would seem like an outrageously high number if we were to see it for this property? So in our case, we've got bulk modulus, and I believe AFlow had it in GPA. That makes sense when you see the numbers. So I would guess, of course, there's not going to be negative values. Maybe for really exotic things. I'm not sure exactly how you define that, but probably no negatives. A high bulk modulus value, probably 400s as high as you'll see, maybe a little bit higher than that. And your average is going to be about 100 or 200. But we can double check this. We can run this, and here we go. This is the distribution. This is our bulk modulus values on the x-axis, and this is the number of instances that it appears. We've just made a histogram, and we've kind of binned them. I've decided to make 20 bins. We could arbitrarily change this number. If we run it with 40 bins, it changes slightly, but not too much. So we'll go ahead and go back to 20 there. But we can see that, okay, we don't even get up to 400. We get to about 350. We don't have any values below 0, so that's good. And yeah, we're centered at about 100. That seems like a reasonable place to be for bulk modulus. Great. So it doesn't look like there's anything totally off about our data. So we can probably move on here. Now, a more detailed examination of this data, you might want to do something like consider if there's chemical groups. And if there's like distinct chemical groups or distinct sort of systems that we're interested in, we could tag those and use those to help us sort of split up our groups when we do our training and testing. But we're going to not worry too much about that here. And then also what we could do is, if we wanted, we could use auxiliary properties in our learning. So what we plan to do with this is take a composition and, given a composition, try to learn materials science and materials behavior. And then with a new composition that wasn't in our training data, we want to be able to predict that behavior. We could expand this out, though. We could look at not just composition, but maybe something like structure. Now, in this AFlow database, we pulled the information. We had, some rudimentary structural information. If we wanted, we could consider using this in our learning process. Now, if you only wanted, if you wanted to be able to say, hey, I just want to be able to predict from a formula, then you don't want to include this in your learning, because then you'd need this for any future predictions. But if you're going to go through like the PCD and predict all of those compositions, or predict the property for all of those formula, you can get this from the PCD as well, this information. So you have no problem if you include this in the learning process. For now, we're just gonna go with the easy route and we're going to only use the composition to generate our features for learning. So the composition is all we need to learn this material property. Okay, so with that said, we're gonna featureize the data. So essentially what we need to do is take a composition like AG10, S8, SB2, and make it machine readable, make it so the computer can parse and understand it. The easiest way of doing this, we want to be able to give the machine a vector so it can do beautiful math on it. The easiest way would be to list out all of your elements in a vector where each component of that element is like mapped to just a single element. So each component of this vector maps to a single element. So in the case of aluminum oxide, Al2O3, we don't have any silver, but we do have 2 aluminum, so we can put a 2 there. We don't have any of these intermediate elements up until O, in which case we have 3 oxygen. Then we don't have any zirconium. So this vector now uniquely represents this composition, Al2O3. So that'd be the most upfront way of doing it. And then using this vector, you can try to correlate these numbers to the property you have using some sort of machine learning algorithm. Now, we can probably do better, and a lot of people use what's called a composition-based feature vector. So they can take a combination of element and atomic properties, and we'll call this a composition-based feature vector. So that's what they make there. In fact, to make a composition-based feature vector. Perfect. So this can take a little bit of coding. I've supplied that code. It's actually called composition.py. You can go to our file explorer, this file here, and it does this sort of featureization and vectorization for us. Now to use this code, composition.py, we're going to need to store our formula and our target in specific ways. So when I say target, in our case, we're going to try and learn bulk modulus. That'll be an easy one to learn on. So you'll notice up here, I think I failed to mention it. We got our data frame, and we added the formula. In our data frame, we added only the bulk modulus. So we're just trying to learn one property for now. And so we also similarly cleaned our bulk modulus over here. So we're going to need to rename the columns to say formula and target for this specific function we're going to use, this generate features function. And I believe if we hit Control I on that, oh, it's saying there's no documentation available, but we can go ahead and open up the actual file itself. If we go to this generate features, we need to input a data frame where it's a 2-column data frame, and the column values are formula and target. So it's telling us what we need to do there. So we'll go ahead and just rename this data frame cleaned so that the columns are now formula and target as opposed to what they currently are, which is formula and bulk modulus. So I'm going to go ahead and run that. So I'll rename this here, and that changed to target. And now if I run this function here, I'm going to get a matrix that holds my features. So we can go over that once it's made. And I'm going to have the target for each of these rows. So for each feature, it'll be mapped to a target here. And then I'll also return the formula that are associated with the feature and target values, or the bulk modulus values. So I'm going to get that running. So this red box up here means it's running. And then it returns this little statement, this sentence. It says the element Pu from this chemical formula is not currently supported in our database. So if we come back up here, X has 2,335. It used to have df cleaned. So X came from df cleaned. It used to have 2,336. So this single composition, it didn't work. We were not able to vectorize it properly, so we drop it when we return this matrix of features, this feature matrix X. So X is capitalized because it's a matrice. That's sort of like convention. This is just an array, so it's lowercase and similar here. So let's go ahead and open it up. We can look at this data frame and we can kind of get an idea on how we featureize this thing. So the first column, let's go ahead and grab formula, open that up as well. So the first column here is the average atomic number. And that's associated with this formula here. And the second column is the average economic weight. Still, all this first row is associated with this formula here. So you can kind of move through there. And you can see how we kind of went through this, average crystal radius, average electronegativity, and then we go further, and some of these are the sum of the number of unfilled p valence electrons, and we go further and we get the variance in the number of unfilled p valence electrons, and we go further and we get the range of the thermal conductivity. So we just have a lot of composition-based descriptions of this chemical formula, and we did just simple math operations to sort of build a vector that's like one of these rows is a vector that represents the formula associated with that row. We can build a vector that does a decent job of explaining or telling us about that composition. And then we're going to try to correlate that vector to the actual property or target we're trying to learn, in this case, bulk modulus. Okay, so up to this point, we have cleaned the data. We've briefly looked through the data to make sure nothing looks crazy. We've featureized the data. We've turned the compositions into some machine-readable vector that means something, that can be correlated to reality. And now we're going to make a train test split. So when we do machine learning, what we're going to run into is if we have data, we can learn on that data and we can do arbitrarily well on the training data. So think of 6 or 7 data points and then think of fitting those 6 or 7 data points with polynomial. If you're allowed to just change the order of your polynomial, first degree polynomial, regardless of where those data points are, it might do okay. If your data is perfectly lined up, you might be doing perfect already, and you'll say, okay, great. But if it's, if your data is kind of thrown randomly on there, second degree polynomial might fit a little better. Your error will go down, third degree, fourth degree, and then when you hit a fifth degree polynomial, you can fit that line through every single data point, or you can do pretty good like that. Hopefully you can visualize what I'm saying here. But that doesn't really mean anything when it comes to the next data point that gets laid down, because your model fit every data point perfect, but we call that overfitting, right? So what we're going to do here is when we fit our model, we're only going to do it on a fraction of the data. In this case, what we're doing with this function is we're splitting our data into a training set and a test set. The test set is going to be comprised of about a third of the data, and the training set is going to be the remaining 2/3. On the training set, we're going to do all of our model fitting. We're going to play with how complex our model is. Think of like the order of your polynomial to try to get the best fit possible. But at the end of the day, we're going to try and be conservative with that fit because we're going to use the test set to say how well our model actually does. Okay, so that sort of keeps us honest and keeps it so that our model it keeps us from like wanting to overfit that model, because as humans, you just sort of tend to do that. So very simply, we're going to make that train test split. And then we're going to move on and we're going to consider whether or not we want to scale the data. So I say consider because really the scaling step is sort of a hack to make to help with for numerical reasons, for numerical purposes. We're going to be doing what's called gradient descent for many of these algorithms, and this gradient descent can sort of break if our features aren't in the same range of values. So a simple way of sort of fixing it is to do this scaling. So we'll apply standard scaling to the features, and that'll make it so that for each column, we can go ahead and open this up. Each column, it's going to scale it so that this has a mean of 0 and a variance of 1. And it does that by calculating what the mean is for the column, subtracting that mean from every single value in the column, and then calculating the standard deviation from this original column, and then dividing every single value in this column by the standard deviation. So that'll give us, or I think it's actually by the variance. So that'll give us a mean of 0 and a variance of 1 for every single column. So it'll repeat that for each column. And then for each row, some of these rows, we're going to make a vector for each row. And we don't want any specific instance of data to be more important than any other. So what we'll do is we'll just normalize these rows. We'll make them so they all have, so they're all a unit norm. So that'll be as easy as calculating the size of the vector associated with each formula and then dividing, yeah, dividing each one of these by that norm. Okay, so to implement this, we're going to make an object that holds a standard from this standard scalar class. We're going to make a normalizer from this normalizer class. So the scalar object is going to need to learn the mean and the variance of the training data so that we can make the mean and variance one. So we're going to fit it. So this x train scaled, the scalar is going to be fit to the x train and then transformed. So we're going to fit the scalar to x train, and we're going to transform x train by the fit. So this is kind of obtuse. An easier way to do it might be scalar dot fit on x train. So we're going to figure out the statistics of x train with this function here. And then we will actually change x train so that it matches this mean of 0 and variance of 1 using this transform. So this line just sort of does both of those at once. Now, once we've fit to x train and transformed x train, we can transform x test as well. But we're going to want to use the training statistics because we don't necessarily know what x test is going to be in the future. So we want to make sure that we can do all of this sort of analysis using just the training data. So x test is going to be transformed by the statistics of x train because scalar has, with this fit function, stored the statistics of x trains, and it's going to transform x test here. Then similarly, we're going to do normalization. So the fit part doesn't actually matter for normalization, but people keep it in for workflow purposes. But we're going to take x train scaled, and we're going to normalize it so that it's a unit vector for each formula. And we're going to take x test scaled and normalize it again so it's a unit vector for each formula. Now, I say consider scaling the data because some of these algorithms that you could use don't do gradient descent and don't require scaling. So in our case, things that do generally need scaling, linear regression, ridge regression, lasso regression. Those are all sort of the same thing with different, slightly different implementations. Support vector machines, those almost always need scaling. Neural networks usually need scaling. Logistic regression, so it's like a classification tool, almost always need scaling. And these all use some sort of gradient descent. Now there's closed form solutions to a couple of these, but those are a little bit slower with large numbers. So even then people use gradient descent. And then for the algorithms that do not need scaling, usually they're just decision-based algorithms. So decision trees, random forest, gradient tree boosting, et cetera, et cetera. Okay. Now, this chunk of code gets our train test split, and then it scales our data using that train test split so that we can actually do some machine learning. Now let's actually do that machine learning. So we're going to select the algorithm we want to use. In our case, I'm going to be borrowing from the Burgos group, a good publication you can reference up here if you want to see how to do this. They predict super hard materials in this publication using bulk modulus predictions using machine learning. So I'm going to follow them, and I'm going to use a support vector regression to get these values. So in the support vector regression model, we're going to want to be doing parameter optimization because there's what's called regularization. It's the extent to which we limit model complexity, and we're going to want to play around with that. If we let our model get too complex, it overfits. If we let our model be too simple, it doesn't learn anything. So we want to find the beautiful spot there. So to do that, with our training data, we're going to split it again using what's called cross-validation to get these little like small chunks of training and validation. And if you don't know what cross-validation is, that's one that you can just quickly Google and read about. It's not worth really going over in here. But essentially, this is making like a mini train test setup so that we can see how well our parameters are doing on data they weren't trained on. Now, for support vector regression, there's parameters we're going to go over. Most importantly are usually this C parameter and this gamma parameter. C is essentially how hard you penalize something for being wrong. So if I penalize you really, really hard for being wrong, you're going to overfit so that you're not wrong so often. And gamma is the influence a single point has through space. So it's sort of like a way of multiplying my error by each point and how close it is to my best fit. Okay, so these parameters, I'm going to define them in a log space around what I know are generally good parameters. So C equals 10 and gamma equals 1 usually works okay for learning with a composition-based feature vector. And so I'm going to search parameters centered around that. And importantly, I'm going to search them in a log scale. So we want to span several orders of magnitude. So as a parameter changes, the performance doesn't change so much, but it changes pretty fast in log space. So that's where we'll look. So we're going to go from 10 to the negative 1 to 10 to the third with steps of 5 for the C parameters, that's centered around 10. And then for the gamma parameters, we'll go from 10 to the negative 2 to 100 with steps of 5. So we're going to look at each combination of these two parameters. And then what we're going to do is we're going to store these parameter candidates in a dictionary. So this is a Python dictionary with curly brackets. My key, this first value here, is going to be the argument I want to put into my actual model. So if I were to do model equals SVR, I have these arguments I can put into the model, and one of them is C, so that's going to be our key here. And then another one of them was gamma, right here. So I'm going to go ahead and put this key as gamma. So when I put this dictionary can now be used as the arguments to a function if we do stuff fancy. And then finally, with this function here, this is taken from the sklearn model selection module, the grid search CV, and kfold is also taken from there. With this, I can tell it, here's a model that I want to do grid search on. I can tell it, here's the grid or the candidates I want you to search over. And then I can tell it, this is the cross-validation scheme I want you to use to ensure that we're not overfitting. So you can go ahead and run this, and I'll start talking about the next few lines. Sorry, I got to run all the way from here. Oh, I guess I didn't run any of this. Okay, so we're going to run all of that, just the code we talked about. So here we're going to define the grid search, and then here we're going to actually perform our grid search. So what I have here is this object I've defined, which told it what type of model we want to use and what type of parameters we want to look over and what type of train and validation split we want to use. This object here, we're now going to give it the data that it can optimize on. So we're saying, using our X-train scaled data and our Y-train data, go through this model with these parameter candidates, with this splitting scheme, and give us the results of a grid search, which is essentially just training the model over and over and over with each combination of parameters and testing that model's performance using this cross-validation output. So when it's finished, the grid is going to be an object with important attributes associated with it. And specifically, we want just the best parameters. So it's going to score them with an R2 score. And the parameters that resulted in the highest R2 score are going to be saved onto this attribute here. So we're going to go ahead and make our own variable called best parameters, and we'll extract that from the grid object. And then we'll go ahead and print those out. And then once the grid search is done, it's also going to plot the grid search and how each parameter did. So here we go. So the best parameters we found were a C of 100 and a gamma of 1. So that's right here. And then the plot of this shows us how we actually did. Low C values generally don't work. High gamma values generally don't work. Oops. Looks as C gets higher, our results generally improve, and gamma generally gets better as it gets lower, but around 1 is sort of the sweet spot. and it said that this box here was the best one we could find. I'm satisfied with this grid search, so I'm going to move on. So at this point, what I've done is I've cleaned my data, I've looked at my data, I've scaled the data so I can use it with gradient descent based algorithms. I've decided to use a support vector regression. With that regression, I searched a number of parameters. I searched 25 different parameter combinations for this C parameter and this gamma parameter. I found the best combination of those parameters using this grid search CV. And I saved those best parameters so I could use them for later. And then I plotted it just to see visually if I seemed to be in a local maximum and things weren't going to get that much better. Okay, so now I know what parameters work the best for this data. And so I want to create some final model using those parameters. So I'm going to go over here. I'm going to do my final model. It's going to be a support vector regression. And this fancy star best parameter says, using these keys, match them to the arguments in your function. So if we look at SVR and remember those arguments, one was gamma. So match the key to gamma, match the key to C, and input the value of those keys. In our case, best parameters. Let's go ahead and look at that. So best starts with the B. Best parameters input the value of those keys as arguments to this function. So we did good there. So we're going to essentially be doing the same thing as SVR C equals 100 and gamma equals 1. We're doing the same thing with this line as we are here. I'll go ahead and delete that. So we're defining the architecture of our final model. And then with our final model, we're going to actually fit it to X-train scaled and Y-train. So now that model is fit to this data. So we can go ahead and run these two. And so once the model has been fit to that data, we can generate predictions on our actual test data. So I'll get our y-test predictions here. And then plotting it, we can see how well we did in a general sense. So excellent results. This is the actual DFT bulk modulus values. These are our predicted DFT bulk modulus values. And all of this data was from the test set. So it was all withheld during training. So that's great. And then to get a better idea in terms of solid numbers, how we did, we can go ahead and define our score as the R2 score between these two values and our root mean squared error calculated between these two variables. So if we look at y-test, it's a big array. Y-test predicted is an array with the same dimensions. And we can go ahead and print those off. So we see that we actually got an R squared of 0.92. I'm going to add one more decimal there. So 0.919. And we have a root mean squared error of 17. So great performance overall. So that's the basics of how you make a model, but let's take it one step further now. Something that's not actually brought up very often. Let's go ahead and predict with new compounds with this model. So to do that, I've implemented this chunk of code. And the idea behind this code is what it does is it saves the model you built. So when you initialize this object, you're going to give it the model that you trained. In our case, it would be final model. You'll give it the scaling associated with the training data of that model, and you'll give it a normalizing object just for workflow purposes. And then when you give it that, you can build a bulk modulus model, essentially. So I gave it my final model, my scalar, and my normalizer, and it built a bulk modulus model. And then with that built model, bulk modulus model here, we can do dot predict and insert a formula or a list of formula. So we can insert a formula as a string or a list of formulae. And when we insert that into this function predict right here, what it will do is it will look at the formula. It'll automatically convert it to feature vectors. And then it will use those vectors, put them through this model, and generate predictions. So if we go ahead and run this, we get our bulk modulus model here. So that's the object and where it's at in memory. And then we can go ahead and define these. We have this list of formula to predict. And we can run this here, bulk modulus model dot predict these formula. and it's going to return the predictions for those formula. So we had NaCl, Pu2O4, and NaNO3. So if we go to our bulk modulus predictions up here, you'll notice that it dropped Pu2O4. And that's because Pu2O4 is not supported in this database. So this element is too obscure or rare for it to have a significant amount of elemental properties. So it's just not included. But what you can also see is for the ones that are available and that it can convert into feature vectors, it returns our predicted values. And just for the sake of showing you, we can also do this for a single string. When we run it, we get just the value for the single string. Okay, so that's it for this walkthrough. If you have questions, you can go ahead and email me at kutikawe@gmail.com. So this is my email. And beyond that, good luck getting started in doing machine learning and material science.